Velocity from an equation for height. Rocket is fired vertically and follows h of t measured in feet with time t measured in seconds. H of t equals negative 16t squared plus 560t. Determine the speed of the rocket at t equals 3 seconds. Okay? So this is basically the kinematic equations. As a slight cross-training, exploring outside of your bubble, which is, I'm all for thinking inside your bubble. But, all right, so the idea here is if you have a constant acceleration, so acceleration equals dx squared, second derivative of position with respect to time. And if that is a constant, we'll say, call it g for gravity. I'll call it a for acceleration. So if you have a constant acceleration, so like gravity, then you could find the position v of t by taking the integral, which would be at plus v naught. And then you can find the position, I'll call it x of t, by taking the integral again, which would be 1/2 at squared plus v naught t plus x naught. Where the v naught here is that constant you always seem to get with integrals. And that constant in this case would be the initial velocity. And then this x naught would be the initial position. So it'd be like, well, where are you at? Well, part of that depends on where you started, which seems reasonable. And that kind of looks like what this equation follows here. The gravity is 9.81 gravity meters per second squared, but that's also pretty much about 32 feet per second squared. And so 1/2 of 32 is 16. So that's probably where this equation came from. That's a surprisingly straight line there. Okay. So there's enough daydreaming. Back to focusing. Determine the speed of the rocket at t equals 3 seconds. Okay. So we have a position, which we're kind of magically given. But this is kind of the derivation of where it came from. And so we took the derivative to get the derivative of velocity to get position. No, integral. Took the integral of velocity to get position. So we're going to want to take the derivative of position to find speed. So speed is measured in feet per second. And we're given feet, which is the position here. So we want to take the derivative. So h prime of t equals negative, was that 32? Yeah. Negative 16 times 2 times t plus 560. There we go. Which equals negative 32t plus 560. And what it wants us to do is plug in t equals 3. So basically what this is saying is this rocket shoots off at an initial velocity of 560 feet per second, and then it's slowing down the higher it gets, which seems almost reasonable. So h prime of 3 is 560. I'm just going to move these around real quick because it's easier to have the subtraction on the right side. It just feels more normal. I don't like to start off an equation with a negative sign. Just something not very wholesome about that. So 560 minus 32 times 3. So we have 96. 3 times 3 is 9. 3 times 2, yep, 96. Carry the 1. Nope, I'll change colors. Boom, boom. 5. So 10 minus 6 is 4. 4. Add 1 there, so we have 15. 15 minus 9 is at 6. So 464. 464 feet per second. Let's see what we got over here as possibilities. Aha, 464. So looking at some of the other options, yeah, they're all about the same value. Except for this one right here. Trying to trick you with the, ooh, probably shouldn't circle that. That's the acceleration. Acceleration equals negative 32 feet per second squared. All right, 464. That's the answer. And the idea here for a rocket shooting up with a equation for the position. So if you take your position, which is measured in feet or meters or whatever, cubits? Anyway, feet, you take the derivative of feet, or derivative of feet with respect to time, and you'll get feet per second, and that'll give you your speed. So you take the derivative of your h of t function, plug in whatever value you want for time, and that will give you the speed at that given time. Excellent. So that works for velocity for an equation for height.